For our new lesson for today, we're going to be working on u-substitution, which is essentially the opposite of the chain rule. So notice we have up here, it says if you take derivatives of more complex expressions, we frequently have to use the chain rule in order to differentiate. The equivalent when we're talking about integrals is called u-substitution, and it allows you to integrate expressions which do not appear integratable. Now, this technically we could integrate using the power rule, but it doesn't seem very fun because we'd have to multiply out x squared minus 1 to the 5th power, essentially multiplying it times itself 5 times, and then distribute an x to all of that. Finally, when we were done with all that, then we could actually take the integral. But I think there's an easier way to do it, and it's called u-substitution. The steps are the same every single time we do a u-substitution problem, so you kind of have to just follow along the first couple times we do it, make sure that you see the pattern in the steps, and then we'll go from there. So step 1 is always to figure out what the inside of the function is, and we did this when we were talking about chain rule as well. Typically the inside of the function appears either inside of parentheses or inside of a radical, or maybe grouped in the top or bottom of a fraction. Maybe it's inside of a trigonometric function, etc., etc. So you're looking for the inside function. In this case, inside function is x squared minus 1 because it's inside of those parentheses. So the first thing we're going to do is we're going to set up our u. So we have u equals x squared minus 1. And we're going to start making some substitutions in just a minute, but we'll kind of get everything set up to begin with. I also need to know the derivative of u, because essentially to take this integral, I'm going to go ahead and change the variables around so that they work essentially the way I want them to work. And so we're going to change everything to be written in terms of u instead of keeping them written in terms of x. So the derivative of u, du, is going to help us get rid of this notion of dx in just a minute, and you guys will see that. Now, I'm not going to do this every single time, but let me just kind of show you real quick how this works in terms of like why we have a du over on the left-hand side and why we have a dx on the right-hand side. So let me show you the long way the first time we do this. Let me erase this really quick. So typically for u, we would say it's du dx because we're taking the derivative of u with respect to x. And we would say the derivative of x squared is 2x, and the derivative of negative 1 is 0. Now, if I multiply both sides by a dx, multiply by dx, on the left-hand side, I'm just left with a du. On the right-hand side, I have 2x dx. Now, typically, from now on, I'm going to eliminate that middle step, and I'm just going to jump straight to that last step. Because I don't need to show the multiplication every single time of dx, I just wanted to show you one time so you kind of knew why that dx was over there on the other side and where that du came from as well. So let me start to highlight some stuff so it becomes apparent how we are doing these substitutions. So first things first, x squared minus 1 is equal to u now because I have defined x squared minus 1 to be equal to u. So what I'm going to do is I'm going to rewrite this integral, but this time I'm going to rewrite it with a u inside of those parentheses to the power of 5. And again, I'll try to keep it all simplified so you can see this. So that u and that u. So x squared minus 1 here got replaced with u here. Now, we still need to get rid of all of the other stuff in this original equation. So notice that I still have an x here and I still have a dx here. So I can't have any traces of x left over when I'm doing my u substitution. So in order to get rid of those two variables, we need to substitute them down here from the second equation. So here's kind of where you get to play a little puzzle, I guess you could say, in the sense of what do I need and what do I not need. I need to replace dx, so I'm going to keep dx right where it is. I need to replace this x, or substitute this x, and get rid of that. So I'm going to keep this x right where it is. But I have this extra 2 that I don't need, and so I don't need this 2, so I'm actually going to move it over to the other side. And the way I'm going to do that is by dividing it over to the other side. So I'm going to divide by 2 on this side and divide by 2 on this side. That way I can say this is 1/2 du is equal to x dx. Now, before we do this next substitution, let me be very clear about the commutative property of multiplication, which says that it's okay that this x and this dx are completely separated by all this stuff in the middle, because multiplication says it doesn't matter, the commutative property says it doesn't matter what order you're multiplying in. Multiplying, for example, 2 times 3 times 4 is the same thing as multiplying 4 times 2 times 3. So just because these are separated by this vast expression in the middle doesn't mean that it's not the same thing as this. So x dx is literally the same thing as x dx up here, even though it's separated by this gap in the middle. So let me highlight that. This x dx is going to be replaced with, or substituted by, 1/2 du. So in my equation over here, I'm going to write this as a 1/2. I guess I should write it next to each other just to make sure we're all clear. I'll write it as 1/2 du. So again, just to make sure we're all on the same page, the x dx that I had in my original equation is right here, x dx. I am substituting that for what it's equal to, 1/2 du, because I want to have everything in terms of u's. So here you see 1/2 du is taking the place of these two orange highlighted pieces, the x dx. Now, again, I will start to do little shortcuts as we go here and there. So notice that I wrote it all here at the back just because I wanted to show you how it kind of got multiplied. But typically this 1/2, I'm going to pull it out eventually anyway. So typically I'll just start writing it out front. 1/2 times the integral of u to the 5th power du. So make sure that you're convinced that this is the same thing as this, because 1/2 is a constant multiple. I can just pull it out front. And that way when I take the integral, I get 1/2 times the integral of u to the 5th, which is u to the 6th over 6 plus c. If I simplify that, I get 1 over 12 u to the 6th plus c. And last but not least, we are not allowed to leave our final answer in terms of u. We always want to go back and substitute what u is equal to. So if I come back up here, way up here at the top, you'll notice that u is actually equal to x squared minus 1. So for my final answer, instead of leaving it as 1 over 12 u to the 6th plus c, I'm going to rewrite that as 1 over 12 times x squared minus 1 to the 6th power plus c. And that is my final answer. So that's a brief overview of u substitution. We'll do a couple more examples together just to make sure you guys get the hang of it. But try to follow like the patterns every single time. You guys will notice that the patterns are very similar and don't change too much, that we do the same process as we go through each problem. Alright, so for this one over here, I'm going to decide what my u is. And again, u is typically the expression inside of grouping symbols. So in this case, my u is going to be 3x minus 2. I need to take the derivative. Du is equal to 3, because the derivative of 3x is 3. The derivative of 2 is 0. And then dx. Remember I said I would start taking that shortcut, where instead of writing du over dx equals 3, and then multiplying the dx over to the right-hand side, I'll just keep it there right now. So let me start to do some highlights. 3x plus 2, or sorry, 3x minus 2 is going to get replaced with this 3x minus 2 equaling u. I need to replace this dx, because I want everything in terms of u, so I have a dx right here. But notice that I have that 3 in front of it, and I do not need this 3 because I don't have any extra 3's to replace. So to get rid of that 3, I'm going to move it over to the other side by dividing, so that becomes a 1/3 du equals dx. So now there's my substitution. Again, I could write this right next to each other. So I could plug in u for 3x minus 2, and that becomes u to the 4th. And then I could replace dx with 1/3 du right here, But eventually I understand, and I hope you're starting to understand as well, that this 1/3 is just a constant multiple. It just tags along for the ride. So I'm actually going to pull it out in front now. So I'm going to leave that 1/3 out front. And it's the integral of u to the 4th du. And again, let's make sure we're all clear on where that came from. The u to the 4th came from replacing 3x minus 2 with what it's equal to, which is u. And the du came from replacing dx with what it's equal to, which is 1/3 du. So there's my 1/3 du that I have. All right, so now let's take the integral, now that we have a much simpler problem to work with. The integral of u to the 4th is u to the 5th over 5 plus c. If I simplify that a little bit, I get 1 over 15 u to the 5 plus c. And then last but not least, I don't want to leave my answer in terms of u. I want to go back to being in terms of x. So this is 1 over 15 times 3x minus 2 to the 5th power plus c. And I will leave my answer like that, now that that's in simplest form. All right, for this next one, we have an inside function again. So let me draw a line right here and we'll do our work over here. Our inside function is 5x minus 2 du is equal to the derivative, which is 5, and then dx. If I start to make some substitutions, 5x minus 2 is going to get replaced with u. Notice that I do want my dx to get replaced. So here I have dx. That's going to get replaced in just a minute. But I do not need this extra 5. I have no extra 5 over here that's needed. So I'm going to get rid of that by just moving it to the other side. By dividing, that's 1/5 du is equal to dx. And therefore, when I do that, now I have just my dx over here on the right-hand side of my equation, because that's all that I want to replace from that. Notice that everything else is highlighted except for, of course, this overarching function of the square root, just like over here, the overarching function of the 4th degree. And on the previous one, the overarching function of the 5th degree were the only things left. That's okay, we can leave the actual function there because we're going to use that to take our integral in just a minute. I just don't want any variables left over, if that makes sense. So, let's do our substitutions. This 1/5 is a constant multiple. I know it's going to be, so I'm just going to pull it out front. Times the integral of the square root of 5x minus 2 is going to get replaced with u. And then dx is going to get replaced with 1/5, which I already accounted for in the front of my integral, and then du. In order to take the integral of this, I just want to quickly rewrite this as u to the 1/2 du. The integral, therefore, is 1/5 times u to the 3/2 over 3, and then halves would be 3 times 2. Remember, we talked about that in the video 2 videos ago, where if I'm dividing by a fraction, instead of working with that complex fraction, I can divide by the 3 and then multiply by the 2, plus c. If I simplify this a little bit, I get 2/15 times u to the 3/2 plus c. And last but not least, I do not want to leave my answer in terms of u, so I'm just going to resubstitute back in what u is equal to. So that's 5x minus 2 to the power of 3/2 plus c. Or, if you wanted to write it as a radical, that would be 2/15 times the square root of 5x minus 2 cubed plus c. Either one of those is a fine answer for me. You can leave it in either one of those two forms. Alright, let's try some more. Again, if you want to try to challenge yourself a little bit, maybe pause the video and see how much of this you can work out on your own, and then come back to check your answer. For the first one, if I want to find my u value, it's what's inside the parentheses. So u is equal to 6x minus 1. The derivative du is equal to 6 dx. I don't need that 6. I do have a 4, but I'm actually going to pull the 4 out, and in addition to that, I'll pull that 6 out. So the way to get rid of it is to divide it to the other side. That's 1/6 du is equal to dx. If we start to do some substitutions, 6x minus 1 is going to get replaced with u. Dx is going to be replaced with 1/6 du. And then the only thing that's left really is this 4. So again, I'm going to pull that 4 out front. So I'm going to write it as 4 times, remember the 1/6 is a constant multiple, so it's also going to get pulled out front. The integral of this 4 we pulled out front already, so don't worry about that. 6x minus 1 is getting replaced with u, so this is going to be u to the 2/3 power. And then dx is getting replaced with 1/6 du. I already accounted for the 1/6, so now it's just the du part. If I multiply 4 over 6, I can simplify that to 2/3. The integral of u to the 2/3 is u to the 5/3, bump up the exponent by 1, divided by 5 times 3, because I don't want to deal with the complex fraction, plus c. My constant multiple out front, I have a 3 here and a 3 here, so those are going to divide out to be 1. So that leaves me with 2/5 u to the 5/3 plus c. And last but not least, if I want to replace u with what it's equal to, that gives me 2/5 times 6x minus 1 to the 5/3 power plus c. And again, same as the previous lessons, if you are unsure or not quite confident that these are the integrals that work, go backwards and actually find the derivative of this, and it should come back to what this is up here. You'd have to use the chain rule to find the derivative of this, but it should end up there. Alright, for number 5. My inside function, what's underneath that radical, is x squared minus 2. My du, the derivative, is 2x dx. Notice that I want to get rid of my dx, and I want to get rid of this x, so let me start to highlight what we're getting rid of. The x squared minus 2 is taken care of there. The x dx is taken care of here. I just have this extra 2 I don't want, so I'm going to move it over to this side. Notice, by the way, the extra things that I have are always constants. So like it's a 1/5 when I move it over, or a 1/2, or a 1/4. It's never like x over something, or whatever the case may be. So keep that in mind, is that you should never move variables over. If you're moving variables over, it probably means we're not doing it correctly, just because that would give us more x's in our final answer. We only want u's in our final answer. Perfect. So now that's getting replaced. Excuse me. Now the x dx is getting replaced with 1/2 du. If I do my substitution, again, that 1/2 is a constant multiple, so it's going to tag along for the ride out front. This is the integral of x dx is getting replaced with 1/2, which I already took care of, and then du, so I'll put that du at the end. And then inside of the square root, I have the square root of x squared minus 2, which is u. If I rewrite that, that's 1/2 times the integral of u to the 1/2 du. That's 1/2 times u to the 3/2 over 3/2 plus c. My 2 here and my 2 here are going to simplify out to be 1. So this is 1/3 u to the 3/2 plus c. And if I work backwards to put that x squared minus 2 back in, that gives me 1/3 times x squared minus 2 to the 3/2 power plus c. And if you wanted to write this back in radical form, since it was giving it to us in radical form, that would be 1/3 times the square root of x squared minus 2 cubed plus c. Either one of those last two answers would be acceptable. Either one of those. All right. All right, I believe this is our last slide for today. Maybe not. That one's our last slide for today. All right, we have 2 more slides, so 4 more problems. I am going to go ahead and pause the audio portion. So I'll work out all the work for you, and you guys can pause the video in a minute when I show you the work so you can check your answers. I'm just not going to walk through it step by step. So I want you guys to try and do these 2. The first one is definitely doable, number 6. The second one's also doable, but there's some rewriting before you take the integral, so make sure that you are clear on where that comes from. So again, I will have you pause the video here and attempt both of these problems, and then when you have answers, unpause it and see if you got them correct. Alright, so here are the answers to both of them. And again, if you got them right, great. Go ahead and move on. If you didn't get them right, take a minute to pause the video and kind of see the work and see if you can figure out where you made an error or a mistake somewhere in your work. On the second one specifically, I said it was a little bit trickier because you have this cubed root of u on the bottom. And so when you bring it up to the top and rewrite it, you just have to rewrite it as u to the negative 1/3. That was really the only tricky part about it. I just wanted to make sure that you guys were able to see that's not on the top of the fraction, that it was in the denominator. So again, take a minute to look over this and make sure that you are clear on where these answers came from. And then we'll move on to our last slide. Alright, here we go. So we are going to look at both of these. And we'll do them together, and I'll actually talk through them just because there's a little bit more in-depth work involved. Same process, just a little bit more in-depth work. So I'm going to erase this one just so I have more room. We'll come back to that. We'll come back to that one. So for number 8, the inside function u is equal to x to the 3/2 plus 2. du is equal to 3/2 x to the, if I lower that exponent by 1, that will be 1/2 dx. Now I do want that x to the 1/2 in there, and I do want the dx in there. So I need to keep the x to the 1/2 here, and I need to keep the dx here. But I don't need this 3/2. So I'm going to get rid of it by multiplying it to the other side. Or I should say dividing it, but multiplying by the reciprocal. So that gives me 2/3 du is equal to x to the 1/2 dx. So if I start to highlight what I'm able to get rid of, I can get rid of those. I can get rid of x to the 1/2 dx. And now if I make those substitutions, I have 2/3, because that's a constant multiple that comes out front, times u to the 9th power du, which is now a much nicer and prettier equation to take the integral of. So this is 2/3 u to the 10th power, if we bump up the exponent by 1, divided by 10, plus c. If I simplify a little bit, that gives me 1/15 u to the 10th power plus c. And if I replace u with what it equals, I get 1/15 times x to the 3/2 plus 2 to the 10th power plus c. And again, to convince yourself, go back and actually make sure that that derivative makes sense to you if you took the derivative of that. Alright, so let's come back to this other one. I'll erase this u work over here. There we go. Alright, so for number 9, you have that u is equal to the inside function. Now notice that I have some parentheses here, and then I have a square root here. And I told you guys that the inside function is typically inside parentheses or inside of a square root. And if we have both of them, you have to decide which one of them should be u. My hint to you is that we're taking derivatives of u in order to replace other pieces. And so because of that, typically we go with the higher polynomial or the higher exponent because we're able to take the derivative of that to get rid of some of the smaller ones. So what I mean by that is we should make our u equal to the quadratic because the derivative of a quadratic will be linear. So my du will help me to get rid of this linear part. So u is equal to x squared plus 4x minus 3. Du is equal to 2x plus 4 dx. Now, if we start to notice things that are in common, that's going to get replaced. I have this dx and this x plus 2 I want to get rid of. Now, my dx is here. I don't know if you guys recognize or not where the x plus 2 is inside of this, but essentially there's a GCF of 2. If I factor out that GCF, I would be left with 2 times x plus 2. So there actually is that linear function x plus 2 in here. I'm just going to get rid of that 2 and move it over to the other side. So that's 1/2 du is equal to x plus 2 dx. Now I'm able to highlight that whole thing to get rid of it. If I make my substitutions, this 1/2 is a constant multiple. It tags along for the ride. I'm going to bring it out front. That gives me the integral of the square root of u du. And again, let's make sure we're all clear on where that came from. X squared plus 4x minus 3 was replaced with u. So underneath that square root, we have that. X plus 2 times dx. X plus 2 times dx is replaced with 1/2 du. So I have my 1/2 and my du. If I rewrite this, I get 1/2 times the integral of u to the 1/2 du, which is 1/2 times u to the 3/2 over 3/2 plus c. My coefficients, the 2's will divide out to be 1. So that's just 1/3 times u to the 3/2 plus c. If I plug in what u is equal to again, I get 1/3 times x squared plus 4x minus 3 to the 3/2 plus c. And then last but not least, you can leave it like that, or, and I'll write it over here, or if you want to write it as 1/3 times the square root of x squared plus 4x minus 3 cubed plus c. Either one of those would be a correct answer. All right, I think that's it for today.